Okay, hello. Mm, let's begin, I suppose. So the audio seems to be working and the video is working as well. Let me just raise the volume a bit. I'm not sure if it's perfectly. Faryal, is all audible? Okay. Right, so let's begin. So we were talking about orthogonality and the dot product being zero. And so now let's tie all of that back into the central problem of linear algebra, that is to solve the system Ax equals to B, right? And today we're going to talk about it, a problem. For example, we know what to do when we have a solution, right? So when we're doing Ax equals to B, we've talked in detail about what to do when we have a solution. We know how to do Gaussian elimination and we get to that solution. And if in the case of infinitely many solutions, even then Gaussian elimination is able to tell us what the solutions are. Okay, so we can build solutions. Now, the particular case that we want to talk about today is what if Ax equals to B has no solution, right? Now, on the face of it, if the system has no solution, why do we, what does it even mean to try to solve it, right? Because if it doesn't have a solution, why are we going to spend some time on it? But let me demonstrate using an example that we solve Ax equals to B even when it doesn't have any particular solution. We do still try to solve it, and we try to solve it in some approximate way, in the best possible way that we can. For example, consider the problem of the linear regression, right? Excuse me. Consider the curve fitting problem, right? The curve fitting problem. And the problem is as follows. Let's say you have, excuse me, sorry, let me just get some water. Okay, hopefully that's better. Um, so the problem is as follows. We have, let's suppose we are trying to, we do this in statistics all the time, which is, let's say we have a bunch of points, point 1, point 2, point 3, and we can see that they're sort of in a line, but not really, right? They're sort of going upwards and they're following the trend line that we call, but they don't all exactly fall into one line. For example, if I draw a line through these points, then the other three won't be on that line. And similarly, if I draw, let's say, a line through the first 2 points, then maybe I might get the third point, but these two won't be on that line. Let's suppose I draw another line and try to satisfy these 2 points, then the rest of the points won't be on that line. But still, we draw this line that we call, let's say that line is like this, and we call this the line of best fit. And what we've done here is essentially we've solved a system of equations. We've said Ax equals to B. We've solved that system even when it had no solution, right? And how have we done that? Let me just demonstrate. So each of these points have some coordinates, right? So x1, y1, x2, y2, x3, y3, x4, y4, and so on. And we are saying that this line, if this line has equation y equals to mx plus c, then I wanted to satisfy all of these points, which is of course not possible, right? But if it were possible, let's say there was some line, some imaginary line that could satisfy all of these points, then what would be the equations that we wanted to solve? The equations would be as follows, right? So if I write the equation of the line y equals to mx plus c, then I can substitute all of these points into this line, and we can have the following set of equations. So y1 is equals to mx1 plus c, y2 is equals to mx2 plus c, y3 equals to mx3 plus c, and so on. So I'm trying to solve this equation for these variables, these m and the c. I'm trying to find a line that I can define by a gradient and an intercept such that all of these points fall on a line. And I already know that that's not going to be possible. But if I make a system out of it, that system of equations is going to look something like this. It's going to look like it has two variables, m and c, which I want to solve for. And on the right-hand side, I have these data points y1, y2, y3, up until yn. And on the left-hand side, I have the coefficients of m are x1, x2, dot, 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 xn, and c just has coefficient 1, so 1, 1, dot, 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 1, right? And I already know that this system has no solution. So this is my Ax equals to b, and it has no solution. It can't possibly have a solution, because if it had a solution, then all of these points would have exactly been on that line, right? And yet, we still, in statistics, we find this line of best fit. So the question really is, how do we get this line of best fit? And so the short answer is that in statistics, what we do is, instead of solving Ax equals to b, we don't solve that equation, and we solve a modified equation called the normal equations. And that equation is not Ax equals to b, that equation is A transpose Ax is equals to A transpose b. That is, we multiply both sides by A transpose, right? And so the rest of this lecture is really going to talk about, where does this equation come from? How do we know that this is the right equation to solve? And how do we know that solving this equation, how do we know if it even has a solution? And how do we know that solving this equation will give me this line of best fit, or the best solution in the case when Ax equals to b has no solution, right? So that's the overview of what we're going to do today. So let me rewrite the problem. The problem is Ax equals to b has no solution, right? And this tends to happen a lot. Notice that we're dealing in a case where there's lots of equations and there's just two variables, right? So this is usually something that we run into when we have m greater than n, right? Okay. So what do we have now? The question really is, let's rephrase that problem. If Ax equals to b has no solution, recall that when it does have a solution, I can think about it in terms of the column space of A, right? When we say that if Ax equals to b has a solution, this is something that we've talked about from lecture 1, that when Ax equals to b has a solution, it's the same as saying b is in the column space, of which means if it has no solution, then what I really mean is that P is not in the column space of A. So let's try to visualize that. So let's say we have the column space of A. Let's say it's a plane like this, right? That's the column space of A. And now I want to solve it. I want to solve the equation Ax equals to P for a vector that's not really inside this plane. So the problem that I'm running into is that this vector B comes out of this plane. So there's really no combination of vectors within this column space that I can combine to give me this P, because the linear combinations of the columns of A are restricted within this plane. So I can't solve that equation. Okay. So the way to go forward, so what do we do now? The idea is then to find, if we can't solve Ax equals to B, what's the next best equation to solve? That's what we're trying to think about. And so within that, when you ask the question like that, so what we're really asking is that, is there a vector, what vector in this column space is the closest possible vector to this vector B? And the closest possible vector to this vector B within this column space is, what about if I take this vector and if I project it, right? If I break it into two components, let's say there is one component of this vector which is inside the column space, and the remaining part is this part which is perpendicular to the column space. Okay, let's try one more time to do a good job of making this perpendicular. Nope, I really am terrible at this. Okay, this is the best I can do apparently. Okay, and so the idea is that I've broken this vector B into two vectors. This part of it now lies within this column space, and the rest of the remaining part is perpendicular. And so I'm going to call this P, which is basically, the idea is to project, P is the projection of B onto the column space of A, right? And let's call this vector E. So the idea is P plus E will give me B, which means P is basically, or rather E is basically B minus B. Okay, so that's really what we're talking about. And the idea is that the way I've constructed this is that E is going to be perpendicular to P, but also to the whole column space of A, right? Okay, so that's the next best equation that we can solve. So if we can't solve it for Ax equals to B, then what we can is to take as much component of B as we can within the column space, and then the remaining part that we can't really solve for is called E. We've called it E because this is the error, right? This is the part of our vector that is still sticking outside the column space and which we can't solve for. So instead of solving Ax equals to B, the idea is to solve Ax equals B, right? Okay. So what can we do? How do we solve this equation? To try to find the answer to that, we go into the one dimension. So let's consider the 1D case, right? We're going to move down to one dimension so that the problem is nicer, the problem is easier to solve. And so in the one dimension, a column space basically looks like just a line, right? So we have some vector A that is defining, this is the vector A which is defining this whole space, and I have some vector B which is outside this line, which means it's something like this. And now I want to project it onto A. So this is P. Sorry. This is P, this is P, and this is again E, which is P minus P. Okay, so in the 1D case, what we see is that P is on the same line as A, which means P is just a scalar multiple of A, right? So P can be just written as X times A, where A is a vector, X is a scalar, right? So A times X or X times A. That's the idea. Okay, and what else do we know? We know that the vector A is perpendicular to this error vector E, P minus P, right? So we talked about perpendicular or orthogonality in the last lecture, which was how do we codify this mathematically? And the idea is, well, when two vectors are perpendicular, the dot product is really zero. So A dot product with E is going to be zero, which can be written in other words as A transpose. E can be written as P minus P equals 0, and we then write it as A transpose P minus XA is equals to 0, right? And that's really the equation to solve. So now if we want to find this projection, the idea really is what is this X, how much A is being scaled by to give me this projection vector. And so how do we solve this? The way we solve this is extremely simple. This is an equation that can be easily solved. So we write this as A transpose P minus, remember that A, B, A, these are vectors, X is just a scalar. So I can write this as X times A transpose A is equals to 0. And so we can rewrite this equation as follows. We can say A transpose B is equals to X A transpose A, which gives me X is equals to A transpose B over A transpose A. So that's really the solution in the 1D case, because we were looking for how much AX is equals to P. So this was really the solution that I was looking for. So that's easy in the one-dimensional case. How much do I need to scale this A by to give me this best projection vector? And what's the projection vector in this case? The projection vector is just X times A, right? A times X. And that can be simply written as A times, now that once we have the solution, we can write it as A transpose B divided by A transpose A. Okay. All right. So there are two ways to viewing this equation. The first way of viewing this equation, this formula for the projection, is to think of these three components: this first component, this second component, and this third component. Notice that we know that P is a vector. So viewed like this is some vector. This is A transpose B is just a scalar. The dot product of any two vectors is just a scalar. And this is also a scalar. So this is, in one way, you can see that this projection vector is nothing but A being scaled by some scalar, which is actually the scalar X. But there's another way of viewing this equation. If we know that vector matrix multiplication is really associative, so I can multiply things in any order that I want, as long as I don't change the order in which they're written. So if I view this as A transpose divided by A transpose A times B. So now what do I have? Over here I have a number, but on top I have A transpose, which is not a number, it's a matrix. This is the outer product that we discussed in the last class. So A transpose is actually the outer product of A with itself, and it's really a rank 1 matrix. It's just one column being multiplied by one row. So this gives me a matrix. This entire thing is a matrix which is being multiplied by a vector B. So this is just a vector. So in terms of the B vector, now we say that P is just simply some matrix, capital matrix P, times P, which over here I'm going to call this P matrix. So this is this whole thing, this whole matrix, I've given it the name of P, and I'm going to call it the projection matrix. So the idea is that if you have a vector that is sticking out of your subspace, then if you can multiply it with the projection matrix, then it will give you the projection with vector inside your space. Okay, so these are the three important things. So this is your scalar that needs to be multiplied with. This is really your solution. This is the formula for your projection vector, and this is the formula for your projection matrix. And that's, so you see, in the one-dimensional case, it's really easy to solve, because in the one-dimensional case, it's just you're not solving ax equals to b, you're solving ax equals to p, which in the one-dimensional case becomes you're solving small a x is equals to p. It's a really nice, simple equation to solve. It's a one-dimensional, one-vector equation to solve. Okay. What's next? Now that we have some understanding of what's going on in the one-dimensional case, let's go back. So let's now go back to the two-dimensional case. And the two-dimensional case is all we're going to need to derive a formula that can get us to n-dimensional. So let's come back to the case where we have a two-dimensional space. There's a vector sticking out. Why don't I just copy the equation that I already nicely. So let's take this picture that I already have and let's plug it in here. Okay, so I'm trying to solve this geometric image now. So let's say this is a two-dimensional space. This is really a plane. So I can say in this case, what I'm really trying to solve is I'm trying to solve the following equation. I'm trying to solve P is equals to, if P is in the column space, right? If P is in the column space, then P can be written as the linear combination of the vectors in this that are spanning this space, right? I know that if it's a two-dimensional space, this is a plane, then of course it must be spanned by two vectors, right? So maybe there's a vector A1 here, and there's a vector A2 here, and the linear combinations of these two vectors A2, A1, I know that the basis, and let's say that the basis for this plane is given by A1 and A2. Okay, so I know that if P is in the column space of A, then P can be written as XA1 plus XA2, right? Okay, and which can be really easily written as P equals to AX. This is just a linear combination where I've just put these A1 and A2 in a nice matrix form where A1 is the first column and A2 is the second column, and X is simply the X1, X2, the vector X1, X2. So if I multiply both of these together, I get the same equation, X1A1 plus X2A2, right? Okay. P is projection of B onto C. What does this mean? It means, Faryal, that the idea is that since B is outside this column space of A, we're really looking for a vector that we can solve for. So I'm trying to break down, if you remember your physics vectors, if you've taken it, or I think even in calculus, you know that if you have a vector, let's suppose, any vector V, you can try to break it down into, you can resolve it into components, right? The way you resolve it is, for example, if you're in two-dimensional space, then you can resolve it into two components, an X component and a Y component, right? Such that both of these components are perpendicular to each other. That's what I'm trying to do with P. I project it so that I resolve it into two components. One is vector P and the other is vector E, such that both are perpendicular to each other. And the idea is that now I have got a component of B which is in this column space. So that's what I mean when I'm saying that I'm projecting P on P is the projection of B, right? Does that make sense for you? Yes, if A is perpendicular to E, then their dot product gives us 0, right? So I talked about this in the last lecture that when you have perpendicular vectors, we know that their dot product is going to be 0. So if A is perpendicular to E, then A dot product with E is 0. Okay. All right. So let's come back to the two-dimensional case. And so in the two-dimensional case, the first thing that we figured out that the projection vector can be written as A times X. Okay, what else do we know? The other thing that we know is that this projection, this B vector, if I project this, then this vector E that I have, it's going to be, this E is going to be B again, which I can really write as B minus A times X, right? So I know that E is going to be, in this case, A1 is going to be perpendicular to E, and A2 is going to be perpendicular to E, because both of these vectors are also in the column, are the vectors that are making the column space, right? So this E vector is really, if I put the E vector here, you can notice that if you just put the E vector here, then this is perpendicular to A1. If you put it here, you can see that this is perpendicular to A2, right? And so how do we write these two equations down? Well, the first one is A1 transpose E is simply B minus AX, which is going to give me 0. And A2 transpose B minus AX is equals to 0, right? And this is, you can start to see how this is going to turn up into a matrix equation. I can write these, notice that A1 and A2 were the columns of A. A1 transpose and A2 transpose will really be row vectors now. So I can write this equation as A1 transpose, which is a row vector, A2 transpose, which is a row vector. Write it down like this in matrix form. That's the first two equations, writing down. And the second component is the same, which is B minus AX, right? So this is B minus AX is equals to 0. And this equation, this matrix that we've just constructed here, where the columns of A have become the rows of some other matrix, that's just the transpose matrix, right? So this is just equation is saying A transpose B minus AX is equals to 0. And at this point, we're just ready to see that this equation simply becomes A transpose B minus A transpose AX equals to 0, which gives me the equation A transpose AX is equals to A transpose. Okay, this is the normal equations. These are the normal equations in matrix form. And the idea is that we're to solve this system, instead of, since we know that we can't solve this system for AX equals to B, this is the equation that I wrote at the start of the lecture, which was A transpose times AX is equals to A transpose. This gives us, when you solve the system, it will give you this line of best fit. Okay. All right. So this is the equation to solve. Let's think about a couple more things. Let's take this equation A transpose B minus AX, and let's think about this equation for a moment. In the context of our null spaces and our four fundamental subspaces that we had, what's this equation saying? If I consider this to be just a vector B minus AX, this is a vector, A times X will be a vector, so A transpose some vector V is equals to 0. What is this equation saying? This equation is saying find the solution to A transpose V equals to 0, which is just, remember, a solution to this. This is a homogeneous equation. That means this V is in the null space of A. And let's not call it V, we already have a name for it, right? We have the name E for it, which means that E is in the null space of A transpose. And remember when we drew that picture, which was the big picture of linear algebra that Professor Gilbert Strang has taught us, which is that if you have the column space of A, then that's perpendicular to the null space of A transpose, which means if there's a vector E in the null space of A transpose, then E is going to be perpendicular to the column space of A, which is really both the things that we really needed, right? We were looking for a vector E which was perpendicular to this column space of A. And that's exactly what we wanted in terms of solving our equation. Okay, so that's another way of looking at this equation. Okay, so now the question is, let's come back to solving this equation. We found the equation that we want to solve. The question is, can we solve this equation? How to solve ATAX is equals to A transpose B. The simple answer to that equation, to that question is, well, we want to solve it for X, right? We want to solve it for this X vector. So we can just simply write it as X is equals to, let's take this matrix on the right hand side and we say that we have A transpose A inverse times A transpose B. Now you should be questioning if I'm allowed to take this. The first thing is, do we know that the inverse even exists? What do we really know about A transpose A? So remember that A was an m by n matrix, and in our case we were thinking of a matrix with more equations and fewer unknowns. So it's not even a square matrix. So an inverse is not even defined for a square matrix. But if you consider A transpose A, then you have an n by m matrix being multiplied with an m by n matrix, which gives you a square matrix, n by n. So at least we know that A transpose A is a square matrix. Another thing that we know is that A transpose A is not just a square matrix, but it's a symmetric matrix. It's a symmetric matrix, and the reason it's symmetric is because you take A transpose A and you transpose it, you just get A transpose A back again, right? So it's a symmetric matrix, it's a square matrix. And let's assume that A transpose A is invertible. That's the missing piece before I can start to solve that equation. So now once we know that this is invertible, treat this whole thing as one matrix and then take the inverse on the right hand side. So multiply, let me fill in the step that I missed out, which was multiply A transpose A inverse on both sides. A transpose A X is equals to A transpose A inverse A transpose B. So now I know that if it's invertible, then I have identity on the left hand side, and on the right hand side I have this equation. So that's the solution. That's the approximate solution, right? That's the best solution that I can get. Okay. And in this case, what's the projection vector? The projection vector is, of course, A times X, right? So the projection vector was A times X, as we saw here. So we can write this as A times A transpose A inverse A transpose B. So that's my projection vector. And recall that in the one-dimensional case, this projection vector looks like A transpose A divided by A transpose divided by A transpose A times B, right? So this 1D nice case has a nice analogy in the n-dimensional case where you can you can see that there are similar components. Of course, it's not exactly the same because now you have multiple rows and multiple columns, but it still sort of retains some flavor of taking a transpose and solving that equation like that. And it's something being multiplied by. Where is C? Faryal, your question about where is C, let me see if I mentioned any C. If you're talking about this notation here, this I mean by the column, let me read your question. So P is a projection of B onto C. It's not onto C, it's the column space of A. This is column space of A. Okay, so that's what I'm talking about. All right. Okay, so A transpose divided by, right. So that's the equation. And let's just complete this discussion and bring in the projection matrix. So this was the projection matrix, right? Because you can see P as capital P times P, and over here that's the capital P is just given by A times A transpose, A inverse times A transpose. Okay. All right. A couple of properties that I missed out on, which we can discuss now about this projection matrix. Let's think about the idea of projection, right? So firstly, think about this projection matrix. Over here in the 1D case, we had the projection matrix as A transpose divided by A transpose A. And let's think about what will happen if I take the transpose of that projection matrix. It really shouldn't change anything, because consider in the 1D case, if I take the transpose, then that's just A transpose transpose, and in the denominator you also have A transpose, which doesn't really change things because it becomes A transpose whole transpose, and sorry, these are being multiplied, so you can, it's just the same thing again, right? A transpose A. So that's nice. That is, it becomes, this one was, the first component is coming from A transpose whole transpose. So remember that we change the order when we have we have A times B transpose, we get B transpose A transpose. So you can verify that this, taking the transpose on both sides doesn't really change anything. So the first property that we get is that transposing the projection matrix doesn't really change anything. It's the same matrix. And the other property that we can think about geometrically is that if I project B onto this column space once, which is P, so if I've done P is equals to P times B, if I try to do another projection, if I try to do the same projection onto the same column space, so notice that P is already in the column space, which means if I try to project P onto C of A, I shouldn't really get anything different. I should get the same thing because P is already in the column space. So there's no other component that we can remove, which means it should still give me vector. Project P onto CA gives P itself, which means if I take P squared, it should be the same P. That is, if I take P squared, if I take P times small p, projection matrix times the small vector P, I should still get P. So that means it gives me P is equals to capital P times capital T times P, which is P squared P. Okay, so these are the two nice properties. I think might have confused you, but that's the idea, that transposing it gives the same matrix and squaring it gives the same projection matrix, right? So these are the two properties that we can verify in this case as well. So let's try to find P transpose in this case. Well, that's A transpose, A inverse, and A transpose Let's try to transpose that, and when we transpose the whole thing, that's just A transpose whole transpose. So we change the order. The last vector, the last matrix becomes the first matrix. Then we have A transpose A inverse whole transposed, and then we have A transposed. The first matrix A transpose whole transpose just becomes A. The last matrix is A transpose. And remember that if you inverse and then take the transpose, it's the same as transposing and then taking the inverse, which means inside it just becomes A transpose A. You just take the transpose of this A transpose A, which is A transpose transpose A, inverse, and we get the same thing back again. A transpose A, inverse, A transpose. Did I do that correctly? No. So this was A transpose, and this was A transpose or transpose. So that just gives me the same thing again, which is this is the P matrix. So we verified that P transpose is the same as P, and we can try verifying the second property as well, which was P squared. Now P squared is going to be A. Let's write the matrix once. So A transpose A inverse times A transpose, and let's write the whole thing again, which is this is P, and this is another P, right? So A times A transpose A inverse times A transpose, and now we get A times A transpose A inverse. So parentheses don't matter because it's matrix multiplication is associative, and we get this form, this nice little form. And over here we can notice that we have this matrix A transpose A, and the same matrix is inverse, right? This is A transpose A, and this is the inverse of A transpose A. So when I have a matrix B being multiplied by its inverse, I know that I get the identity matrix. So this just becomes the identity, and I can cancel that out to get A times A transpose A inverse, A transpose, which is just P. P squared is equal to P. So those are two nice properties of the projection matrix that we've verified in the matrix form as well. Okay. All right. I'm going to take a couple of minutes break. So break. And then we'll resume the lecture. Okay, we are back. Let's get rid of this. Okay, so let me summarize what we went through in the first half of the lecture. We started off by discussing what can we do when we have a system that has no solution. And the answer was that if it doesn't have a solution, we can try to find the best possible solution, the best approximation that we can. And I gave you immediately how we get that solution. We say, let's not solve ax equals to b, let's solve this new equation, right? And then we discussed where this equation comes from. I gave you the geometric idea, and then we went to the one-dimensional case, and then we got some equations. We went back to the two-dimensional case, we built up an equation, and then finally we had this equation A transpose AX equals to A transpose B. And then I said that if you assume that it's invertible, that this matrix A transpose A is invertible, then you can solve this equation. And this, if you can solve them, then this is your solution to X. And let's not call it X, let's call it X hat now, right? So let's put a hat on this. The reason I'm putting a hat on this is because we did not solve the original system AX equals to B. If we had solved that, then that would have been the solution X. Instead, what we solved was the new system A transpose A X hat equals to A transpose B, right? So this is a notation that you usually use in statistics by putting in a hat on the approximation, right? Okay. But I made an assumption here that A transpose A is invertible. And now I need to answer, at least I need to discuss a little bit about when do we have that case. The question is, when is A transpose A invertible? And the first answer is that, of course, A transpose A is invertible when we can just look at it in terms of the matrix A transpose A, and we already know that if it has independent columns, if this whole matrix has independent columns, or if we have the non-zero determinant, or it has the trivial solution in the null space, then that tells me that this matrix is invertible. But can I know something about the original matrix A that can tell me when this A transpose A is invertible, right? And so I'm leading to this fact, this theorem, that is, if A has independent columns, then A transpose A is invertible. Right? We're going to see that using some examples, and then we'll prove this as well, and that would be the second half of this lecture. Okay, so the question is, when is A transpose A invertible? Let's take, we were talking about solving an AX equals to B case where M was greater than N for this matrix A, right? So let's take a matrix A which has independent columns, right? So let's build a matrix which is, let's say, 2, 1, 2, and 3, 0, 1. I think those two are independent. Yeah, so this is my matrix A. And now let's look at what we get when we multiply this by A transpose A. So this is my matrix A. Let's just put it on one side. So I'm taking an example here now. Let's do this example. Okay. And so that's my example number 1. And let's try to do. So what does A transpose A give me? Let's transpose this matrix. So I get 2, 1, 2, 3, 0, 1 multiplied by 2, 1, 2, 3, 0, 1. Okay. So let's compute this. So this is a 2 by 3 matrix. This is a 3 by 2 matrix. And so the result is going to be a 2 by 2 matrix. And so let's figure out these entries. So first entry is what? 4, 1, and 4. So that's 9. Second entry is 6, 0, 2, 6 plus 2, 8. And the second entry, this is 3, 0, 1, 2, 1, 2. I know that A transpose A is symmetric, right? So anything off the diagonal would be symmetric. So I know 3 times 2, this is just going to turn out to be 8. And then this diagonal entry, 3 3s are 9 plus 1 gives me 10. Right? So this is a symmetric matrix that I get. And you can see that A transpose A, you can immediately see that A transpose A is invertible. How do I know this? Several reasons. Well, the columns are independent. 9, 8 is independent to 8, 10. Another way I can see this is that the rows are independent. Another way I can see this is that the determinant, the 2 by 2 determinant that is easy to compute, which is 90 minus 8 times 8, which is 64, is not equals to 0. So I know that this is an invertible matrix. Okay, let's do an example in which it doesn't have, in which the matrix A doesn't have independent columns, right? So let's say I have 2, 1, 2, and now I'm going to make the second column dependent on the first column. So this is 4, 2, and 4. So I can see that the second column is just a scalar multiple of the first column. And now let's compute A transpose A. So this is 2, 1, 2, 4, 2, 4, and 2, 1, 2, and 4, 2, 4. So what do I get? I get this entry is going to be the same, which is 9, 2, 1, 2. Okay. And this entry is 8 plus 2 plus 8, which I think gives me 18, right? And this entry also gives me 18. And what about this entry? This is 4 times 4, which is 16, plus 4, which is 20, plus 16, which is 36, I believe. Okay, and this matrix now, you can see that this matrix is not invertible. And the reason this is not invertible is that the first column is just the multiple of the second column. You can see that 1836 is simply 2 times 9 times 18. So in an example, I've seen that if I have 2 examples. In the first example, when A had independent columns, A transpose A turned out to be an invertible matrix. When A had dependent columns, then it turned out to be a non-invertible matrix. So this fact, it seems like it might be true, and so let's now just end this by proving it. So let's try to prove. We have a theorem, and I believe this is, I think, the first time I'm doing a proof of a theorem in this lecture. So if A is invertible, if A can't be invertible because it's not a square matrix. If A has independent columns, then A transpose A is invertible. Okay, and how do I know this? Well, firstly, let's talk about when is A transpose A invertible. A transpose A is invertible when A transpose AX. I want this to have only the trivial solution, right? I want this equation, A transpose A is invertible, is the same as saying that the null space is trivial, right? This is something that these were equivalent statements that I've discussed in several lectures before. So if you don't recall them, you can check out the previous lectures. That invertibility of a matrix is closely related to the null space having a trivial solution. Because if you have multiple solutions in the null space, then you know that the columns are not going to be independent. Okay. How can we get x equals to 0 in this case? The way we can get that is to multiply. So I want x equals to 0. Somehow I need to make sure that x is equals to 0, that x is only the trivial solution. So I multiply by x transpose. What do I get? I get x transpose A transpose AX is equals to, on the right hand side, if I multiply by x transpose, doesn't matter, I still get the 0 vector. Okay. All right. What does this get me? Divide this left-hand side into two parts. On the right-hand side, you have A times X. On the left-hand side, you have X transpose A transpose. And if you remember how transpose were taken, remember if you take AX transpose, then that's just X transpose, A transpose. So you can write this part, the left part of this left-hand side, as AX whole transpose and AX is equals to 0. So this is a vector, and this is really telling me that the dot product of these two vectors is 0. So if I want X to be 0 in this case, I really want AX equals to 0 to be true, right? Okay, so I've decided that if I want let me just recap what the reasoning was. The reasoning was that if I want A transpose A to be invertible, I need to ensure that it only has the null space, only has the trivial solution. So I need to ensure that the solution, the only solution to this system is when X is equals to 0, right? And the way I did that, I just took X transpose and multiplied it by both sides, and I got to the point that I must have A times X is equals to 0. And if again, my original goal is to have X equals to 0 be the only solution. Now, if X equals to 0 has the only solution, which means the null space of A, so X is equals to 0 is the only solution to this problem, only solution to this, then I am assured that A must have independent columns, right? For this to be true. When A has independent columns, then X is equals to 0 is the only solution. So we've worked sort of backwards in this proof, and now we can sort of work this reasoning out forward, which is that when A has independent columns, so I'm now working in the right direction that I should have been in the first place. So A has independent columns, which means AX equals to 0 has only trivial solution, which means AX transpose times AX equals to 0 only has trivial solution, which gives me that A transpose AX equals to 0 only have trivial solution, right? So I've sort of worked backwards from the same kind of reasoning. Okay, so, but the point of all of this, the point of doing this proof and the point of doing this example was to give you an idea of when you can do this, right? So there's even the question of being able to solve. So we said that if you can't solve, so in this lecture we discussed if you cannot solve AX equals to B, you can try to solve A transpose AX is equals to A transpose B. That's the equation that you should solve, and you can solve this. You can solve this if A has independent columns. That's really the main idea of today's lecture. If A has independent columns. Right. That's the main idea of the lecture here. Okay. Let's see. Yeah, I think we've covered all that was required. I've done this, by the way, in a more theoretical manner in the spring semester. Over there, I discussed it in terms of the least squares, and I don't want to do that again. I'll just post the same video in the playlist, which is in that video we take the idea of the root of the least squares problem. The least squares problem. And I didn't really use that name today because we didn't really go down that route. We didn't see it from that perspective. But it's really the same ideas being viewed from a different angle, in that other video lecture which I'm going to just post um, in the playlist that's available from my Spring playlist, which is the ideas to think about in terms of the um, distance between each point from the line, and that we want to minimize this distance, right? So I think I'll just end this lecture today. It's a short lecture again. And then tomorrow or on the next lecture, we'll move to the remaining ideas. I think we're ready now to move into inner products and non-spacers, I believe. Okay, that's it for today.